Good day, everyone. Our topic for today is about the Lebesgue measure. But before I present to you the definition of the Lebesgue measure, let's have a recall first on the Lebesgue outer measure. So here's the definition of the Lebesgue's outer measure. So we let here a function m star from the power set of the set of real numbers to the closed interval from 0 to positive infinity. Now this function here is defined by this one. We have m star of a. Take note here, our a is the set. It is a subset of the power set of R. So m star of A is equal to the infimum of the summation of the length. You have here the length of the interval I sub n. Note here that our class I sub n is a countable collection of open intervals with a subset or equal to the union of I sub n, where n is from 1 to infinity. So we have this one. Now the function m star is called the Lebesgue's outer measure. Okay, we note here that the class In is a countable open cover consisting of open intervals of A. So I discussed already in my previous video what an open cover means. Now let's consider here an illustration of the mapping of the function m star. So we have here our m star. This is the function m star that is defined on this. Okay, again. Now let's consider here an illustration of the mapping of the function m star. So we have here our function m star defined by this. So let's have here first the domain of the function. So we know that the domain we have here PR. So actually this is the power set of R, the set of real numbers. And then for our codomain, we have the closed interval from 0 to positive infinity. So consider here the two sets. We have the domain and the codomain. Then the mapping, we have here the function. Our function is m star. So this is our function. Now from here, let's obtain a new function by choosing a smaller domain. So let's have here a smaller domain. Say this is the set script m. Now we know that already that script m is equal to the set E. So here set E is a subset of the set of real numbers such that E is measurable. Okay, so E here is measurable. That is, we mean by this set, script M is the set of measurable sets. So this is the set of measurable sets. So notice here in our domain, we have separated the measurable sets and the non-measurable sets. So that means here in the blue color, we mean here all sets here, which are the subsets of the power set, are all non-measurables. Then here in the green set or class of sets, we have here all the measurable sets. Hello? So actually, we can obtain here the new function restricted to m. Now, we have this mapping from script m to the closed interval 0 to positive infinity. So take note here, we have our function, this one. So this is now our new obtained function from M star. By choosing a smaller domain, script M, which is the set of all measurable sets, that is a subset of the power set of R. So script M is a subset of the power set of R, as you can see here in our illustration. By the way, this function here, the new obtained function, is defined by restricted to script M of E. So here, E is measurable. It means it is a subset of script M. So this is equal to M star of E. So this is the definition now of our defined function from M star. So take note here, our new defined function restricted to script M is obtained from M star, wherein we just make the domain smaller. It is restricted only to all measurable sets. We have here script M. So this is our definition. Now, as you observed here, the restriction of M star to script M, that is here, this is our newly defined function, is the same as M stars, as you can see in our definition, but it is only defined on smaller domains. So it is only defined here on our script M. We have the set of all measurable sets. So now, let me present to you the definition of the Lebesgue measure. So here's the definition. The Lebesgue measure is the function M from script M to this closed interval from 0 to positive infinity, defined by M of E is equal to M star of E. In other words, so our function here, M, is restricted to script M. So as you notice, the Lebesgue measure is the newly defined function, as I have illustrated a while ago. So this was the new obtained function I presented a while ago. So notice here that this function here is the Lebesgue measure. Hence, we can write it here. Since we have here M is equal to M restricted to M, script M rather. So we have this M is equal to this newly obtained function. So we can write this as, we have M, the new function M, from script M to the closed interval from 0 to positive infinity. Now take note here that we let this as M, our new obtained function. Hence, we have this one defined by, so the definition now is M of E. Take note how our function is M. So this becomes, instead of writing this one, this is equal to, we have M of E is equal to M star of E. So we have this one. Okay. It is a function that we have obtained, which is a restriction of a function M star. Now here, take note that script M is the set of all measurable sets. Hence, for this definition, we can say that if E is measurable, so it means it is in script M, then we can say that the measure the Lebesgue measure of E is equal to the Lebesgue outer measure of E. So it means here that if E is measurable, so it belongs to the script M. So if E is measurable, then we can say that the Lebesgue measure of E is equal to the Lebesgue outer measure of E. So we will use this later on. Now let's consider an example. We let E be equal to the closed interval, say 2, 5. But first, we will show that this closed interval is measurable. Or does it belong to the script M? So by Theorem 1.2, I have discussed this already, states here that every Borel set is measurable. In particular, we have open and closed sets are measurable. So we have here closed set. So we know that this is a closed set. So this is measurable. Hence, this belongs to the set of script M. So after that one, since we have showed it already, we can say that this means, we can say that the Lebesgue measure of E is equal to the Lebesgue outer measure of E. Hence, we can write it as this one, M of our closed interval is equal to M star of the closed interval. Follow? Now, what is the Lebesgue outer measure of the closed interval? Recall that by Theorem 1.9, I discussed this already, the Lebesgue outer measure of I, where I is an interval, is just equal to the length of I. Hence, this is just equal to the length of the interval. Follow? And what is the length of the interval? Now, the length of the interval is just equal to L, or it is equal to B minus A, where we have here our closed interval A, B. Follow? Hence, this is equal to, our B here is 5 and our A is 2. So we have here 5 minus 2, which is equal to 3. Now take note here, A is less than B. Since you can see here, we have here our A, which is less than B, which is 5. So the Lebesgue measure, therefore we can say that the Lebesgue measure of this interval is equal to 3. Okay, so that's it. Now let's have here proposition 1.2. So it states here that if the sequence of measurable sets, we have here EI, E sub I is the sequence of measurable sets, then the Lebesgue measure of the union of that measurable sets, EI, E sub I, is less than or equal to the summation of the Lebesgue measure of each set, each measurable set. We have E sub I. And if this sequence measurable, the sequence of measurable sets E sub I is pairwise disjoint, then the equality holds. Now to prove this, we show two cases. So we will show two cases. We have here the first case, we have this one, less than or equal, which is this case, this part here, first part. And then for the second case, we have the greater than or equal before we can arrive at this. So the first case here, this one follows from proposition 1.6. Here is the proposition 1.6. This is discussed already. So we let here A sub n be a collection of subsets, not necessarily pairwise disjoint for this. Then we have this one. So it follows from this proposition 1.6. Take note that we have here each E sub I is a measurable set. Hence, it follows that the Lebesgue outer measure of each set is equal to the Lebesgue outer measure. That's why it follows from this proposition. Now, for our second case, which is greater than or equal, we let the finite sequence. So we let the finite sequence E sub I be pairwise disjoint, measurable sets. Then this case, the second case, would follow from lemma 1.16. So this is our lemma 1.16. This was discussed already. So the second case follows from lemma 1.16. Now, combining the two cases, we get the desired result, which is this one, equality. So we have here a remark. We note here that proposition 1.22, because we have this equality here, this one, we can say that the function m is countably additive because of this one. So that's it. Before I end this video, please note that the Lebesgue measure m is the function obtained from Lebesgue outer measure m star. So we obtained this function from Lebesgue outer measure m star. The only new here is that the domain in the Lebesgue measure is smaller than that of the Lebesgue outer measure. Take note, this function here is defined from the power set of real numbers to the closed interval from 0 to positive infinity. Whereas here, m, the Lebesgue measure, is defined from script m to the closed interval from 0 to positive infinity, where script m here is a subset. This is a subset of the power set of R. Follow? So script m here are measurable sets, the set of all measurable sets. That is, we only consider measurable sets for the domain of the Lebesgue measure. So that's the end of this video. Thank you for watching and listening. I hope you have learned a lot about the Lebesgue measure and the difference of the Lebesgue measure to the Lebesgue outer measure. So God bless everyone.